name is Gupta. I'm a graduate student of Business Analytics and Information Systems from University of South Florida. Today, we'll see a small tutorial using SAS Enterprise Miner. The first concept that we're going to talk about is decision tree. So, we are using a donor data over here. I have already imported the data here. I'm using a data partitioning here. What does data partitioning do? It divides the whole data set into three parts: training, validation, and set, and we can set the percentages through here. Then I have used one decision tree. Let's run the decision tree and see what output do we get over here. If we click on results, we can see the results over here. So if you look into the results here, we can see a decision tree that has been made. We have the depth of 2 because we have already set the depth of 2. Let me show you that. Here, if you go into the properties of the decision tree, here we can see the maximum depth is set to be 2. If we go back to the results, we can see here that our sum squared error is 1429.202. Now, let's go back to our decision tree and change the depth and see what changes it brings. Let's change the depth to 6 and let's run the decision tree once again. If we go into the results and check the decision tree once again, now you can see the decision tree has more depth because you have set the depth as 6. Okay. Here we can see the sum squared error has been lowered to 1409.481, which was previously 1429.202. So we can say that introducing more depth to the decision tree, our decision tree is performing much better than before. Now let's work on our data partitioning. Here I have taken another partition and I have set the percentage as 70, 15, 15 for training, validation, and test set. I have also introduced a model comparison. So let's run this model comparison and see what is the difference we are getting in these two decision trees with two different data partitioning. So here you can see after changing the percentage in the training, test, and validation data set, we are having a significant amount of change in the sum squared error value and all the other attributes. The next concept we are going to learn is neural net. For neural net, we try to learn the ways to optimize our output. Here, if we go into this optimization tab, we can see the training technique. I have already selected back propagation here. This generally selected as default because I'm trying to do a back propagation algorithm. I'm selecting back propagation. And if I go to network, you can see the number of hidden units is said to be 6 here. I have set it as 6. So we will have 6 hidden layers in our neural network. Now let's look at the output of a neural network over here. So we can see we have the sum squared error of 81 in this run over here. Now I have created another neural network with hidden layers as 3. If you go into this network, you can see I have set the number of hidden network as 3 over here. Now let's run the model comparison and see what output difference that we get in this. Here, if you compare our neural networks, we can see that our sum square error has changed. Previously our sum square error was 81, now it has been increased to 82.72. In case of neural networks, it is almost impossible to know the exact number for weight and the number of hidden layers to have the optimal output. For many cases, it is mostly trial and error. The last model that we are going to discuss is clustering. So here I have again taken an import file. I have done the data partition for the 30 and 30%. And I have also taken a cluster, and here you can see I have made the maximum number of clusters is 5. So let's run this and see what happens. In this case, as we have set the maximum cluster limit as 5, so we can see there has been 5 cluster that has been made, and if you roll over here, you can also see the frequency of cluster, that means the number of data points that is inside this specific cluster, which is segment ID 1 over here. Here we can see the root mean square standard deviation for 5 clusters is ranging between 0.53 to 0.63. Now let's change the number of clusters and see what happens. I'll go into the maximum number of clusters here and change this to 10 and run the cluster once again. Now if you go into this mean statistics over here, we can see it has made 10 clusters. Last time we had seen the root mean square standard deviation varied from 0.53 to 0.63, but here we can see it has the range from 0.42 to 0.55. So whenever we increase the number of clusters, the individual data points distance from the centroid becomes lesser. That is the reason why the root mean square standard deviation becomes lesser. Thank you.